Hello everyone, and welcome to another video where we reviewed in depth the solution for an in-class problem. I should warn you that this video is going to be particularly longer than the other videos dedicated to this kind of practice problems. So for this particular problem, we are asked to evaluate equivalences across different compound propositions. But before we get to that, there are two things that I want to make sure we have into account throughout this video. So the first one has to do with the order in which we apply logical operators. So we say here in class that the first one that I'm always going to apply is a not, then I'm going to apply the and, then or and so kind of like hold the same position. I'm going to do whichever of the two appears first if I read my expression from left to right. Then I do the implication. And at the very last, the last one that I'm going to always be evaluating is the equivalence. Similarly, this same logic applies if it happens to be the case that I have multiple, for example, multiple ands on a compound proposition or multiple nots. I'm going to always read them from left to right. And now the second thing that I want you to keep into account is the definition of the four basic propositional argument structures that we discussed in class. So two arguments that are always valid, we call them modus ponens and modus tollens. And these two type of arguments look a little bit like that. They are always valid. And why is that the case? Well, they both start from the very same premise. They have the same premise at the beginning. We establish a causal relationship between a condition A and a consequence B. In the modus ponens, after I have established this causal relationship and I observe the condition here, then it must always be true that if these two things here are correct, if these two things here are truth, then necessarily B should also be truth. And this makes absolute sense, right? So if I have already said, or if I have already established this relationship, and this relationship is true, so remember that is what valid means. It means that it preserves the value of truth. And then I observe this same condition, then by the very same relationship that I defined it at the beginning, then the consequence should also be there. On another part, we have the modus tollens, where a similar logic applies. So again, ignore this little arrow. This is just to mark that this is the first premise. I established this very same causal relationship between a condition and a consequence. And then what I observe is that this consequence does not happen. So this is another premise. So if this consequence did not happen, that necessarily must mean that the condition also did not occur. This would be a safe conclusion to make. And again, it makes sense. If we have established that there is a condition that every time it appears, it results on the consequence, and we did not observe the consequence, well, that probably just means that the condition was not satisfied. Now, similarly, we talked about two very common fallacies, and they are called fallacies because regardless of what the content of my specific statements here and how convincing they might seem, per the logical structure, we cannot actually guarantee that the conclusions are always true. So in both cases, we have a shared first premise here that establishes this relationship between a condition A and a consequence B. And the idea here is that if this was true, and I were to observe here the consequence, then it would not necessarily be truth. It would be a fallacy for me to then affirm that then the condition should also have happened. This is not necessarily truth. And the intuitive way of understanding this is that even though we have established that there is a condition that always results on a consequence, the fact that I observe the consequence does not necessarily mean that this was the one condition that occurred. So there are multiple other conditions competing with A that could have also led to the very same outcome B. So let me think of an easy example that we all might be a little familiar with. And we know that babies cry whenever they are hungry. So if the baby's hungry, the baby will definitely cry. And then I hear the baby crying. I cannot simply conclude from this evidence here that the baby is hungry, because we know that babies cry for a lot of other things. So it could also be the case that the baby is tired. It could be that the baby needs a change of diaper, etc., etc. Here, the fact that the baby is crying is not evidence enough to know that one of the conditions that has already been established to cause the crying is the one that is causing the crying at this particular moment in time. So affirming the consequence is a fallacy, not necessarily truth. Then we have denying the antecedent. Again, same, we establish a causal relationship here between an event A and a consequence B. And say now that I don't observe the condition A. I would be not necessarily correct if I were to assume that that also means that B did not happen. This is not necessarily truth. Let us think again of an example. So let us keep thinking about babies. say that I have established that when the baby is hungry, the baby cries. And now assume that I have just fed the baby, so I am sure that the baby must not be hungry because it has just been fed. It would be incorrect, sadly, for me to assume that that means that the baby now is not gonna cry. Because again, there are multiple other things that can make baby cries. So even if it's not hungry, it might be that it just starts crying now because it needs to burp or because it needs to go to sleep or something like that. So for this particular exercise, we are asked to evaluate 3 equivalences. Let us write them right here. So this is the first equivalence that we have to try. And we are going to do that by building our truth table. So again, we know that in order to build a truth table, the first thing we have to do is identify the atomic propositions that are involved in my whole compound proposition here, my whole structure here. So we have 3 atomic propositions, right? We have A, B, and C. So let us write them down. So these are going to be our very first 3 columns. And now we have to evaluate the number of rows that I'm going to need. So we know that we have this little formula here, 2 to the power of k, where k is the number of atomic propositions. I have 3, so 2 to the third is just 8. And then we can safely write here space for 8 rows. So something like this. So we have here our 8 possible rows. Now we're going to start filling in the values of each atomic proposition. So here, it's easy to conceptualize this as dividing this whole number of rows by half, and we're going to have half of them being true, half of them being false. And then for the next atomic proposition, I would be doing something similar. I would be dividing each of these areas by half and have half of them being true, half of them being false, and again. And then for C, we are simply going to write TF, TF interchangeably. So this is how we build our basic structure for the truth table. Then we start adding our operators by respecting what we just discussed about the order of precedence. Luckily, we have here a couple of parentheses. They are going to help us isolate a couple of the operators. So it is safe to start with this implication here. First, because it's the one that appears on the far left, but that is not really the reason. The main reason is because it is nested by a parenthesis. We are sure that it only involves these 2 atomic propositions. So we have here the first implication. And again, keep into account what we just discussed about argumental structures. We said that implications really can only be tested whenever what I have defined as a condition is true. So this implication can only be judged in these first 4 cases here. And then we're going to look whether it is true that when A is true, B is also true. So we have here 2 cases in which A is true and B is also true. So this is evidence in favor of our implication. But in here we have 2 cases where A is true and B is still false. So this is evidence that contradicts this implication. Then we have here 4 cases in which A is false. This is non-informative of our implication. So we just go back to our default value of truth. Then again, just because I'm going to take advantage of the parentheses, I'm going to do this second implication here. Let me build a little error here so we don't get confused. And again, for this implication, I'm only going to take into account the cases where B, the condition, is true, and that also results on C being true. So what we see here is that these are the instances in which B is true, but only here that also results on C being true. So only here we have evidence in favor for this implication. Whereas in here, B is true, but C isn't. So this is evidence against our implication. And well, the remaining cases, B is false, so we really cannot test these implications in the default of true. And then we move to our next operator. So we have here that the equivalence goes last. So we are asked now to judge the 2 remaining implications. And we know that we have to go from left to right now because there's no parentheses or anything to help us. So we're going to do this one first. And notice how this implication here is really testing the relationship between the first implication that I had, so this column right here, I'm going to signal it here, and the atomic proposition C. So now I am interested in testing this implication by looking at the cases where this implication is true and C was also true. I see that in these 2 cases, the implication was false. So these 2 cases are not going to be informative, so I use my default value true. And then for the remaining cases, well, I see that, for example, let me delete these dots here, here, and here, the implication was true and C was also true. So that is evidence in favor of my implication. But here, here, and here, the implication was true and C was still false. So this is evidence against our implication. And then we move to our next implication here that we have on the right. And this implication is going to focus on the cases where the A atomic proposition here is truth, and that results on this implication being true. So this implication is this one here. So let me remove this. So now I'm going to focus on this case here and this case here, particularly the cases where this is true, given that the condition has also happened. So I'm going to focus here on only these first 4 cases, right? Or rather, I know that the last 4 cases are not informative because A is false, so this is not informative of whether this implication is true. So I use my default values here of true. And then here we know that we have among these all cases where A is true, only here, here, and here, it is a case that the implication holds. So this is evidence in favor of our implication. But here, the implication was still false. So this is evidence against it. And now we're almost ready to finish. So the last bit here that we have is this equivalence sign that we have here. And notice here that this equivalence is standing in between this whole compound proposition here that I had precisely captured on, let me delete this, on my very last column. So this is the implication that I had here, right? And on the other side, we have this other compound proposition that I have nested here on my second to last column here. So I'm only going to be focusing on whether or not it is true that there is an equivalence between these 2 last implications. So this is the only instance where one of my implications is false, but the other one is true. So we know that this is evidence against our equivalence. So it is not the case that this equivalence is always truth, and therefore we would say that these 2 compound propositions are not equivalent. The second equivalence that we are asked to judge looks a little bit like that. So again, let us build our truth table, and once again, we find that there are 3 atomic propositions here, so 3 unique atomic propositions here, A, B, and C. So let us start by building our table, very similar to the way we did it before. Okay, and then we start building our other operators. So again, we luckily have 2 parentheses here that help us differentiate or isolate a couple of operators. So let us start by doing this implication here. And again, for this implication, I'm only going to focus on the cases where A is true and whether that has resulted on B also being true. So again, these 4 cases, A is false, we cannot say anything, so we default to true. And in this case, we have that only here and here, the implication holds, but in the other 2 cases not. Then we move to our next implication here, that now it's only going to take into account the cases where B was true and that resulted on C being truth. So again, this and this and this and this do not provide information. I use the default value of true. Then we move to these cases and we see that only here and only here we have evidence in favor of our implication because B is true and C was also true. But in here, B was true and C was still false. Here, B is true, but C is still false, so that is evidence against our implication. And now we are moving outside of the parentheses. So we know for starters that the equivalence is going to go last, so we're going to ignore that now. And now we have to decide what to do first, the AND operator or the implication. And we know from the order of precedence that we discussed earlier in this video that we should start with the AND. So we're going to place here AND. And this AND here is going to connect this first implication and this second implication here. So I'm only going to focus on the cases where both this column here and this column here are truth at the same time. So that is only truth here, here, and here, but it's false otherwise. Now we can move to our final implication that we have here. And again, for this implication, I'm only going to focus on A and C as atomic propositions, the cases where A is true and that resulted in C being truth. So again, we know that these 4 cases are not informative. We go to our default of true. And in here, only here and here, we find evidence for our implication, right? Because A was true and C was also true. But here and here, we find that A was true, but C was still false. So that is evidence against this implication. Now we are only left with our equivalence sign here. And this equivalence is an equivalence between this little column that I have here and this whole compound proposition. So I'm only going to focus whether the two last columns that I built have the same value of truth. So we find here again that this is almost always true, except for right here, where the AND operator has a value of false and the implication is true. So this is false. So now it is no longer the case that this equivalence always holds. So we would say that these two statements right here are not equivalent. And then the final equivalence that we're asked to evaluate luckily has only two atomic propositions. So it has only A and B. There's no C in this whole structure. So we can safely just put two columns. And now because we only have two atomic propositions, we know that the number of rows is going to be 2 to the 2, so just 4. That's nice. We fill in our table, and then we start identifying the remaining of the operators. So again, I'm going to prioritize whatever is in parentheses. So I'm going to start with this implication here. And this implication is testing whether it is the case that when A is true, B is also truth. So again, here we have no evidence, default to truth. And among these two cases, only in one of them we observe that when A is true, B is also true. So this is evidence in favor and against our implication. Then we move to the next parenthesis. The first operator that we have there is the not. So I'm going to test here not A. And not A really is only going to be truth whenever A is false. So it's going to have the opposite value as the atomic proposition A. So exactly like this. Then we move to our next implication here that it's also nested in a parenthesis. And we are going to now focus on the cases where not A is true, and that also leads to B being true. So again, here not A is false, we cannot really test it, so we default to T. And in here, not A is true, but only here it is the case that that results on B. So this is the only case where we have evidence in favor of this implication, and we don't have that here. Then we have here our AND operator, and this AND operator is going to take into account the cases where this first implication is truth, and this second implication is truth at the same time. So I'm going to only focus on these two columns here. And we can see that that is true here and here, but not in any of these two cases. And now finally, I am able to judge my equivalence. Let me remove this. And this equivalence is going to be made in between the atomic proposition B, so this column that we had on the left part here, and this whole compound proposition that we have just defined in our last column. And we are testing whether the values that we have on these two columns are the same or not. So what we find here is that this is an equivalence that holds every time, right? So we always have the same values. And therefore, we can say that this is the equivalence among the three that we are given for this exercise that holds. So this statement right here is equivalent to this whole compound proposition. And that is all.